Welcome to problem P. Now in problem P, we are trying to prove that it is impossible to describe two different circles about a given triangle. So here we have triangle ABC, ABC, and we are trying to prove that if you put ABC inside of a circle, like we've done here, there's only one circle that will actually go around ABC, touching all the corners. Right? There's only one way, in other words, to circumscribe triangle ABC. And so we're going to try to prove that this is true, and we're going to use a reductio proof. Now, this is not the only way to prove this, although I think that it is probably the most direct. For instance, you could go through the trouble of trying to write some version of 310 into your proof, which would be okay. It would just overcomplicate things, I think. So I think this is probably the simplest way to do it. So let's take a look at it. We begin, let ABC be a triangle inscribed in circle ABC. So ABC here is our triangle. It's also the circle as well, because it passes through those 3 points. I say that it is impossible for another circle to be described about triangle ABC. So we're going to employ a reductio ad absurdum proof here, because those are pretty useful in these kinds of cases where we are trying to prove that something is in fact impossible. For if it is possible, let another circle ABD be described about the triangle ABC. So here I've drawn circle ABD. Now, clearly this is an oval, but again, we have to draw it that way to make it fit because we're trying to actually do something which we know is impossible. So obviously that's not going to be a real circle, but that's how we would represent it on the page. Okay, so we've described it about triangle ABC, so it shares those points, right, such that it does not coincide with the original circle ABC. Because if it does coincide with the circle ABC, we've just proven the point again that there's only one circle that can be drawn about ABC, triangle ABC. So we've made sure that it does not coincide with the original circle, and we've drawn it like this. And we've called it ABD to distinguish it from the other circle ABC. Now, because circle ABC is described about triangle ABC, the points ABC are common to each, right? So this circle here has points A, B, and C on the circumference, which of course correspond to the corners of our triangle ABC. So the circle and the triangle share those 3 points, right? But because the circle ABD, this oval circle here, is also been described about the triangle, it shares those points as well. So what we find then is that the points A, B, and C are common to all 3 figures. It's part of the triangle, it's part of this circle, and it's part of this circle. So all 3 of those figures share those 3 points. Now this is where the problems begin. If the circles ABC and ABD do not coincide, so if they really are different circles, then they must touch each other or cut each other at points A, B, and C. That's the only way that they can have those 3 points in common without coinciding, is they either have to cut each other at those points or touch each other at those points, right? But a circle cannot cut another circle at more than 2 points. We know this, right, from proposition 10. A circle cannot cut another circle at more than 2 points. Which means that one of these points is either going to have to be impossible, or, as we'll see, impossible. So nor can a circle touch another circle at more than 1 point, right? So it's not possible then for this circle to actually just be touching the other circle at these 3 points, right? So what we can't say, well, it's not cutting, it's just touching. That doesn't work either because of proposition 13. Therefore, circle ABD cannot be described about the triangle ABC such that it does not also coincide with the circle ABC. So there we've proven that because it requires 3 points, it requires there to be these 3 points in common, and two circles cannot have 3 points in common without being the same circle. And so for that reason, there's no way to draw two different circles about the same triangle. It just doesn't work. Now, if you were wondering, wait a minute, isn't it possible for a circle to cut another circle in 2 points and maybe just touch at the third point? Because we know that a circle cannot touch another circle at more than 1 point, and we know that a circle cannot cut another circle at more than 2 points. So maybe it's got 2 points that are cut and 1 point that it touches, right? That would give us 3 points, 1, 2, 3. The problem with this is that proposition 10 actually accounts for this, which you may not have realized. And if you wanted to be a little bit more thorough, you could just rewrite proposition 10 into your proof. But basically what you would do is you would simply redraw the figure so that the circle ABC is cut by circle DEF at points B and G, which is in the original figure, but is touched by DEF at N. So rather than cutting, and your book will have the points labeled H and F, right, on the other side, rather than cutting there, where you see point M in your book, it will just touch N instead. So in other words, the figure in your book is something like this one, right? That's on the page. It would just means that this point D would just be, oops, that's not working. That just means that this point D would be touching right there, right, rather than actually cutting here at these 2 points. But the problem is that the argument would remain exactly the same. And so it doesn't really matter whether or not the circle is touching or cutting the other circle. With that exact same argument, and I think pretty much exactly the same wording, you'll still be able to prove that even if it's just touching and not cutting the other circle, it's still impossible, right? Because it's doing more than cutting the circle at 2 points. It's actually cutting and touching the circle at 2 points. Sorry, it's cutting at 2 points and touching at 1 point. That too is just as impossible as cutting at 2 points or cutting at more than 2 points, right? Like we have in this case 1, 2, then 3, and of course the fourth one. So I hope that makes sense. And again, our job is made a lot easier here by employing propositions 10 and 13. But you just have to understand that 10 really does account for this other case that we could think of where we would have a circle cutting in 2 points and then just touching at a third point. That is still ruled out by proposition 10 because, as I said, we could rewrite it. And just with a very slight alteration, that same argument would prove that a circle cannot cut another circle, nor touch it at more than 2 points.